Hi, my name is Justin Solomon. I'm a professor of electrical engineering and computer science here at MIT and a PI in the Computer Science and Artificial Intelligence Laboratory, or CSAIL. Today, I'm here to answer some of the questions that you've shared with us on the internet. Our first question is, can you explain what a Lie group is and how it relates to Pascal's triangle? Lie groups are named after a mathematician by the last name of Lie. In case you're wondering, that is spelled L-I-E. If you pronounce it lie, that's incorrect and quite problematic. It really offends geometry professors. But in any event, a Lie group is kind of an interesting combination of two different parts of math. On the one hand, a Lie group borrows some ideas from algebra. And on the other hand, Lie groups also use some ideas from geometry. So, first of all, Lie groups have some algebraic structure because they're what we call groups. So groups are mathematical objects that essentially have some version of a plus sign. They're like things that we can add, subtract, combine, and so on. On the other hand, Lie groups are also what we call manifolds, which is an idea from geometry. So for a very simple example, think about rotations in the plane. So rotations, we can think of like angles between 0 and 360 degrees. Now, angles do have some algebraic structure, right? It makes perfect sense to ask questions like, what is 30 degrees plus 50 degrees? Right? That's 80 degrees. That's the mathematical structure. But at the same time, we can think of the angles between 0 and 360 degrees as forming a circle, right? So if we start here at 0 degrees and move around the circle, they make angles from 0 to 360 degrees where they loop back on themselves. So on the one hand, our Lie group has some algebra to it. We have some addition structure here. And also, our Lie group has some geometry because it looks like a circle. So our next question asks why machine learning models really struggle with geometry problems as opposed to some of the other modalities where we've seen huge leaps and bounds, like images and text. Now, in general, in machine learning, when we're building an AI model, we have to talk about what's called the architecture, which is essentially the flow of data as it moves into your AI model in this sort of raw format into some final thing like the inference. Now, when we process images, like the photographs that come in on Facebook or Instagram or what have you, the typical models that we use are built on the basic idea of convolutional neural networks, or CNNs. Now, a convolutional neural network makes a really foundational assumption that depends on working with images specifically. Now, when we work with photographs, if we think about the pixel colors, essentially they come into the computer in a big grid of numbers. All the values are stuck on the vertices of this nice lattice. So what happens is when a computer processes an image in a convolutional neural network, essentially a little filter is passed over these pixel colors, which is what's allowing you to build fancier and fancier signals out of the basic input data. Now, unfortunately for us in geometry, when we take in a shape, shapes are what we would call irregular objects. In particular, the most common way to express a shape on a computer is something called a triangle mesh. Now, a triangle mesh is exactly what it sounds like. It's a bunch of triangles that are linked together into a lattice like this. And the basic issue here is that each one of the vertices in this lattice might have a different number of neighbors, they're connected in some irregular way, and oftentimes you can mesh the same shape in many different fashions. Now, the technology for machine learning from triangle meshes is basically in its infancy relative to the technology for understanding images. But my group at CSAIL and many others in the research community are working really hard to bridge that gap. So for example, we see things like Mesh CNN, HodgeNet, DiffusionNet, and other machine learning architectures that are targeted to this kind of geometry specifically. Now, the question also asks about generative AI specifically. In generative AI, the task is not to just like input a shape and tell me what it is, but rather it's to make AI tools that can create new objects. You can imagine really exciting applications for that in geometry, like making 3D printable shapes based on a human readable description. But that's a really, really challenging task. Even so, recently, a lot of new steps have been taken in the research community to really improve upon the technology in this space. Though the basic challenge is that if I want an AI model to generate a shape, not only do I have to deal with these irregular mesh structures, I need to be able to develop machine learning architectures that can actually output things like the topology or the connectivity of the vertices and the edges on this triangle mesh. Now, things like topology are kind of discrete decisions that aren't well suited to the sort of differentiable AI pipeline that we're used to in the machine learning world. Our next question is actually very closely related to the previous one. Essentially, what they ask is the relationship between two things. The first one is 3D shape analysis And the second one is 3D model generation or synthesis. And moreover, they ask about the relationship between these two objects and emerging 3D data sets, which essentially contain tons and tons of 3D objects that have been digitized on the computer. Now, from my perspective, these are extremely closely linked problems. Let's talk about analysis first. So in analysis problems, maybe we're given a shape. So in 2 dimensions, maybe I draw a curve, like this S shape here. And a typical analysis question in geometry might be to identify curvature regions that are large and curvature regions that are small. So for example here, we have lots of curvature. We might say K is really, really big. Whereas here, in this region of the shape, curvature is approximately 0 because our shape looks like a straight line. So in that way, essentially the analysis problem, the input is a piece of geometry, like this S curve here, and the output is some interesting fact about that shape. On the other hand, we work on synthesis problems, which essentially, in some sense, do the inverse of this particular thing. So for example, I could ask a very different question that's related to the first one that looks something like this. Maybe what I give you is some function, like a function from t to curvature. So for example, if we look at our S shape, at the 2 ends of our curve, we have a lot of curvature, and in the middle, it's pretty flat. So I might have some function like that. So a typical synthesis question might ask, does a shape exist that has a curvature like the function that I've plotted on the bottom left here? Now, these are obviously very simple questions when it comes to analysis and synthesis, and the real ones that we want to answer have some statistical or AI flavor to them. In particular, maybe the statistical question is that we input a shape, like a 3D object, and we want to know how to label different parts of that shape. So maybe I take a scan of a human, and I want to know where its head, shoulders, arms, legs are. On the other hand, the synthesis question asks, can I make AI models that create new 3D shapes? For example, can I make new 3D characters for video games that nobody's seen before? Now, we've worked a lot on the analysis problem. Our research group at MIT and many others are really good at developing tools that don't just do things that are mathematical, like compute curvature, but also ask analytical questions like, what is this shape? What are the parts of this shape? How are shapes related to one another? And so on. Now, the synthesis question is still one that we're working very, very hard on, and there are many reasons why it's so challenging. As we mentioned before, of course, synthesizing things like triangle meshes is really hard to do in the differential machine learning pipeline that's become very popular these days. Now, the second half of the question asks about the role of 3D model databases. So in other words, big collections of 3D shapes that have been collected on our computers. Now, 3D model datasets are really important to come up with the link between analysis and synthesis. Because what can we do? We can take a big collection of 3D shapes, for example, scans of all kinds of 3D environments, and we can start to find patterns between them. Like not just computing curvature, but noticing, for example, that furniture tends to have a lot of flat regions. More natural objects like human bodies maybe are more curved. And these kinds of patterns give us clues how to solve these inverse problems that we're going to need on the synthesis side. So I think what we're currently seeing in the technology is that a lot of the ideas that were first applied to analyzing 3D shapes are now getting flipped backward to generate new ones. Our next question asks, what's up with Moreau envelopes? In general, Moreau envelopes show up a lot in the theory of optimization, which is really important in areas like machine learning, geometry, and other parts of computation. The basic idea of optimization is I'm given some function f of x, which measures something about a system. For example, in machine learning, f of x might be the loss function of a machine learning problem, which explains how well your model might perform well on data. Now, oftentimes, our functions f of x, especially in machine learning, tend to be super complicated. For example, let's say that I'm trying to optimize some function to find its minimum, and it looks something like this. It's really, really bumpy. So the task is given this giant function, which usually isn't just one-dimensional, but extremely high-dimensional, and I'm trying to find a point that minimizes my function. Now, this is really hard to do because there are many other points that kind of look like they might minimize my function. And so there's been a lot of mathematical effort to try and find ways that kind of smooth out these local bumps. Sometimes we call these local optima. In other words, can I find some other function that looks like f, but is some smoothed out one that's easier to traverse? And that's where Moreau envelopes come into play. Now, if you're curious and you know a little bit about mathematics, you can define the Moreau envelope as the infimal convolution of a function and a quadratic. But if that's meaningless, that's OK, because it was a little bit meaningless to me too until I looked it up. Now, essentially, here's what we can do. Now, we're given a function f. The Moreau envelope is some other function that we're going to call m lambda f. And I'm going to hesitate from writing the description here because it's a little bit complicated. It has a lot of mathematical symbols. But the basic point here is that it has two properties. One is that the Moreau envelope is differentiable, so it's smooth. In other words, if my original function f has some little sharp points in it, those cannot appear in m lambda f. But the other thing that Moreau envelopes have, which seems to be kind of useful, is that they actually preserve the minima of my function f. So minimizing m is the same as minimizing f, but m is differentiable. On the other hand, unfortunately, the Moreau envelope is a very difficult object to compute, so I think we mostly see it in theory. Now, I chose to respond to this question for one fun reason, which is that it actually is closely linked to one of the research papers from my group here at CSAIL. So it was a little bit surprising to see this question on X. In particular, my student Ling-Xiao Li had a paper at the International Conference on Learning Representations, or ICLR, just last year, which covers a very closely linked object to the Moreau envelope, which is called the proximal operator. This actually sort of looks like the gradient of m, very roughly speaking. And what he showed is that we can use machine learning style techniques, basically neural networks, to approximate these objects really well. Now, Ling-Xiao was applying that kind of machinery to solving problems where you have many objective functions, many minima, and still traversing these very complicated landscapes of objective values. And I'm guessing that the Moreau envelope probably could tell us a little bit about what his technique is doing, even though he was talking about proximal operators. In any event, I'll let you take a look at his research paper to learn a little bit more. So we also have a question that's asking what I think the most exciting problem area or method I've started thinking about in the last year, either in geometry, computer graphics, machine learning, or any other area. Now that's a big question. I'm a professor, so it's my job to think of fun things to work on all day with all kinds of students in many different application areas. But I thought I'd share with you guys a few problems that I find particularly exciting and motivating that our group is going to tackle. Now, first of all, one of the problems that we're thinking a lot about is in the area of what we would call self-supervised machine learning. Now, here's a big challenge in geometry research. Essentially, when we talked about the big advances that we saw in machine learning research over the last maybe 10 years, a lot of that really was specific to images and text, and there's a reason for that, and that's the internet. The internet contains so many photographs and so many labels attached to those photographs like captions that it provided tons of data we could use to train our machine learning models. Unfortunately for us in geometry, that's simply not the case. There's not as much geometry data on the internet, and the data that we tend to have is not labeled. In other words, we might have a ton of computer-aided design models or 3D shapes that we see in some virtual environments, but those shapes aren't annotated with interesting information that AI systems can learn from. So one of the problems that our group and many others in the geometry domain are trying to think about is how can we do machine learning when our data doesn't have a label attached to it? So in other words, if I have a big disorganized data set of 3D shapes, but I don't know what the shapes are, can I still learn something interesting, whether it's how to generate a new shape or even how to classify them, even though they're not labeled? Now, a second problem that we're thinking about a lot in our research group is in a very different corner of geometry. Now, oftentimes when we think about geometry, we think about 3D geometry, like shapes sitting around us in the world that we walk in. But there's also all kinds of other models of geometry that we study in mathematics, and some of them are extremely high-dimensional. Now, in corners of statistics, we often think of data sets as cutting out shapes in very high-dimensional spaces. And actually, a lot of the theory that we've developed in low dimensions for applications like virtual reality and computer graphics are also really interesting and useful in these high-dimensional settings. So one of the things that our group is thinking about and tackling quite a bit is understanding the geometry of learned embeddings. So for example, if I have a really effective statistical model for explaining images or text, can I align these things to one another, like understand when an image is an image of a particular object that's also described in a piece of text? How do I link these kinds of things together? And how do I understand these shapes of these data sets, even though they're drawn from very different domains? Finally, I thought I'd call out one direction that I think is a really exciting one, especially for people in numerical analysis and geometry theory. Now, for a long time, we've been talking about developing AI tools for geometry, right? We want to make intelligent things that can create shapes, label them, model the environment around us, help us navigate with self-driving cars and so on. But also, we can use AI tools to help us solve classical geometry problems. Now, in a particular area of machine learning, people have proposed these things called neural fields and other types of modalities where essentially what we're doing is using things like neural networks to parameterize solutions to classical mathematical problems. So, for example, in geometry, we often talk about geometric flows. Like, how can I take some surface embedded in 3D and then flow it toward a surface with lower surface area or one that's smoother or what have you. This is a very difficult mathematical model to solve. There's no AI involved. But one of the interesting things that we've found is that we can use neural networks as a representation of the unknown problems in this mathematical setting, and that there's actually a lot of advantages to that, because neural networks sort of by construction have a nice smoothness prior, they can express a big collection of functions, and so on. For example, actually, as we're filming this, my student Anna is in Australia presenting a research paper to the SIGGRAPH Asia conference on exactly this kind of idea. In particular, in her work, she's using neural networks not as a machine learning object, but as an object to parameterize the set of barycentric coordinates that are associated to a shape in 2D or 3D. This is just a classic problem that happens in computer graphics that doesn't require any AI at all, but she's getting state-of-the-art results by using these new representations that have emerged in this different community. So those were some directions of research that we're really excited about. Of course, as a professor, if you ask me the same question tomorrow, I'll give you 3 completely different answers, and that's just part of the job. It's so much fun here because I get to work with these brilliant students and colleagues in CSAIL who really solve interesting problems in all kinds of different domains, and all of them, from my perspective, could benefit from a little bit of geometry. Related to that, we can also talk about the links between music and geometry, and there are so many of them. For fun, I thought I would share one particular link that I find to be really exciting and actually is related to some of the tools that we're developing in our group. In particular, there's an area of mathematics that's called spectral geometry, which is exactly that. It's a link between audio and shape. Now, it might seem like music and geometry are not that closely linked, at least on the kind of mathematical side. Certainly, we know a lot of mathematicians that are also musicians. But actually, they are, even in theory, linked quite closely. And here's a good clue as to why that might be. Now, I play the cello, and one of the basic things we have to do on the cello is change the pitch of the string. And if you've ever seen somebody play the cello, or the violin, or a viola, or what have you, essentially, they're all doing the same thing. There are these 4 strings on the instrument. You press your finger down on the string, and that's what's changing the pitch. Now, if you think about it, that is a really simple link between geometry and music. Why is that? Well, when you put your finger down on the string, in effect, you made the string shorter. And of course, whether the string is long or short is basically a geometric measurement. On the other hand, as you made the string shorter, the pitch changed. So there's a very direct link. Let's say that I have a shape in 3D, like a cube. Here's a cube, at least my best attempt at drawing one on this board. And now let me describe a quick experiment to you. Let's say I have this cube, and for whatever reason, I don't know the shape, and my friend has it in another room. So now, I ask my friend to take a hammer, or really a mallet, nothing too heavy, and to strike the side of the cube here. In fact, I can simulate that with the table right in front of me. Now, maybe I'm sitting in another room, so I don't actually see the shape. I don't know how long the cube is, I don't know how big it is, if it has an inside, anything like that. Now, in the area of mathematics called spectral geometry, we ask a question, which is, given that audio signal, in other words, given the vibration frequencies of a shape, can I reconstruct the geometry of the shape? Now, that problem sounds a little bit ridiculous. I mean, I don't think that you could reconstruct the table in front of me without seeing it just by hearing the sound it makes when I knock. But actually, if you think back to that cello string, maybe it's not so unreasonable, right? When I hear the cello, I know what pitch you're playing, and hence I know the length of the string. The question is basically, can I do that in a higher dimension? Now, spoiler alert, sadly for us, the answer is no. There do exist what we call isospectral shapes. In other words, pairs of shapes that are different, but make the same sound when we hit them. But it turns out that that property is exceptionally rare. And so there are actually many algorithms in shape analysis where what they do is they input a shape, they compute its vibration frequencies, and they use those as a way to describe the geometry of that shape. For example, let's say that I have a big database of 3D objects, and I'm trying to solve the problem of shape retrieval. For example, maybe I have like a 3D scan of a person standing in a particular pose, and I want to find 3D scans that I already have on my computer, either of that same person or of people in a similar pose. Now, in the shape retrieval problem, one of the big issues, kind of like some of the other algorithms that we talked about, is the fact that we represent shapes in these weird, irregular ways, like using triangle meshes. On the other hand, a list of vibration frequencies is just a vector. This is an easy thing to search for in a data set. And so what we can do is we take our scan of the new 3D object, we compute its vibration frequencies, and then we can search in our database for other objects that vibrate in a similar fashion. Now that algorithm goes back many decades. I think it was originally called shape DNA, and while it works pretty well for certain classes of shapes, it doesn't generalize terribly well. But these days, we often use that as one of the many features that goes into machine learning models that learn from objects. In any event, this is just one small connection between music and geometry that I kind of like because this is actually a tool we use in our lab, and it's very rigorous. It actually really connects to both the mathematical side and to the design of musical instruments. But this is one of many. Our next question asks me, what's my favorite Bach cello suite? That was a bit of an unexpected question, but in addition to being a geometry professor, I play the cello, so I'm happy to answer it. If you're wondering, there are 6 Bach cello suites in total, but my favorite is number 5. Number 5 is in C minor, if I remember correctly, and I really like it for 2 reasons. One is the sarabande movement is just gorgeous. I mean, it's like playing Bach in a big empty hall. It's sort of lonely and beautiful all at the same time. But the other is that it's really fun to play on the cello for kind of an interesting mechanical reason. If you're familiar with the bass clef in music, it looks something like this. So there's 5 lines in the bass clef. There's the bass, and on the very top line here is the A string on the cello. Now what Bach has you do in the fifth suite, is you take that A string and you actually tune it down to a G instead of an A. It makes it really challenging to play. It feels really unnatural when you play it on the cello, but once you figure it out, it's really fun to kind of play, and you get an interesting tonality that you don't have for most cello pieces. So thanks for taking the time to learn a little bit about geometry with me today, and I look forward to hearing from you soon.